Okay, great. So I will go ahead and get started then. Thank you all for coming. I'm excited to be kicking off the workshop for today. As I said in my introduction, I my PhD was a lot on scheduling and approximation algorithms, and like that's where my expertise lies. But over the past several months, I've been trying to pivot the focus of my research to be on these learning augmented algorithms. So I'm very excited to talk with you about this today because it's something that I'm very interested in, and it's also like very new to me as well. So this talk is meant to be an introduction to the learning augmented algorithms field. Um, and then I'll kind of, end with like a flavor of some of the things that I'm interested in this space. Okay. So for motivation, in theory, we're often very concerned on lower bounds, proving lower bounds on competitive ratios, NP hardness lower bounds, proving lower bounds on the approximation ratios that are possible for problems, lower bounds for runtimes, lower bounds for sample complexities, et cetera, et cetera. And this is all well and good, but in practice, we have many algorithms that are fast and they work pretty well. And in particular, we have algorithms that work so well in practice that they're working better than what our theoretical guarantees tell us are possible to get all the time. And if you think about it, it's these things are going against each other, but there are lots of reasons why these two things can coexist. Why we can have these lower bounds on our metrics, but also we have good algorithms that work well. In practice, worst case instances often do not appear. So often the instances that are serving as our lower bounds for problems are things which are like kind of edge cases or maybe not instances that they really care about in practice. Secondly, in practice, you might actually have like access to additional information about the instance. And this additional information might be something that we're leaving out of our like model in theory land. So that's why you're able to do better than those worst case guarantees. And then lastly, today's instance, like the problem instance I'm solving today, say like a clustering instance or something, might look different than yesterday's instance. Okay, so all three of these reasons are examples of how, these two kind of hands of, in theory, we have these lower bounds, but in practice, algorithms work pretty well, how these things can coexist. And theory has many models of explaining this, in the scope of like, the beyond worst case analysis land. Just to name a couple of them, one would be like average case analysis, or assuming that in online instances, inputs arrive in like a random order. There's smoothed analysis, where maybe you have these like very bad edge cases, but if you perturb them at all, then you land on an instance which isn't too bad. The field of data-driven algorithms, there's like a family of algorithms that you're trying to choose from. And so in this family of algorithms, you'll be given samples of a problem, and then given the samples, you're going to choose the best algorithm in the family. I also wanted to mention online learning with experts because I know that David's going to talk about it later today. So this is a little bit different, but maybe still kind of the same idea of, you have experts giving you advice at each time step, and then you as the player are trying to minimize your regret given the advice. And so learning augmented algorithms kind of fits into the same scope as these different models do, but I hope to explain to you today why learning augmented algorithms maybe can capture a like a very broad range of classes of problems in practice, as well as be theoretically tractable. So that learning augmented algorithms is a little bit newer on the scene, like maybe with the first papers coming in like 2017, 2018, but there's still a lot of room to be done with it. Okay, so just in one sentence, I've said the word learning augmented algorithms a lot, and I haven't told you what it is. So what I'm going to do is give you one sentence about it, and then we're going to look at some examples, and then we'll move into a formal definition. So what this is we're going to design algorithms that have access to a learned prediction. And you shouldn't know what this learned prediction is yet. This should seem very mysterious still. But this learned prediction is something that can allow the algorithm to surpass lower bounds that we know of from our theoretical guarantees. So in two sentences, this is what a learning augmented algorithm is. So as I said, we're going to start off with some examples on learning augmented algorithms first. in particular dictionary search, and then online load balancing, or also called restricted assignment scheduling. And if at any point, I should say, if you have any questions at all, I don't know how the format is in person, if it'll be easy to interrupt me, but please feel free to put things in the chat as well. I'm able to see pretty well if a notification comes up, so I'd be happy to stop and answer that. Because like I said, this is kind of the outline of what I'm doing, but moreover, my goal today is just to give you a very friendly introduction to learning augmented algorithms and convince you that this is an exciting area to work on. So, I kind of glanced at the participants before. I see that, there's like maybe one person who I'm, sure has worked on learning augmented algorithms before. But I think for the most part, this is still an area that people are getting used to understanding and used to really seeing like the very interesting merits of. Okay, so let's get in with it then. Learning augmented algorithms have been used for a ton of problems. These were literally just like, the first things I came up with making this slide yesterday. So today I'm going to talk about online restricted assignment scheduling, which is also known as load balancing, as well as what I called index structures, but really it's just going to be dictionary search. All right, so dictionary search, I'm entering a library and I'm looking for the book by the author Lewis Carroll. I'm looking for like, the Alice in Wonderland book or something. And this library is sorted by the author last name, and it has N books. So we all know, like any intro CS student, we would expect to know this. Like if the best thing that we could possibly do here is to walk in and run a binary search if I knew nothing about what I was looking for. So binary search will take me log n time. Maybe I start in the middle and I find some author with the last name of M. And then I move like roughly halfway through and I find some author with the last name D. And then so on and so forth until I find that book by Lewis Carroll that I'm looking for. Binary search is the best thing that we're able to do without this additional information. But the point is that I know I'm looking for the author Lewis Carroll, and I know that the books are sorted in alphabetical order by last name. So in particular, Carroll's at the beginning of the alphabet. Why should I start looking in the middle when maybe I could do binary search faster if I started to look towards the beginning of the library instead? So you can do this. Maybe I take a guess. I take a guess at where my book is, and I guess that it's around here in this second position. Okay, so I've started a little bit too early. So now I can still move steps to the right. I can move steps to the right by looking plus 2 books further away than where I started at, plus 4, plus 8, etc., until I find a book which has last name after C. So you do this procedure, and I end up at a book that starts with D. And so now I know that my book by Lewis Carroll is going to be between this interval. So it's between my guess and then the book I found that's after it. So what I've essentially done is I've made my problem a lot smaller. Now I can do binary search in this much smaller interval, and it's going to run a lot faster. So I had this initial guess of starting at this book of the last name B, and that was, off from the book that I really wanted by some guess that I'm going to call error. And so this new binary search you can show uses order log error steps. And experimentally, you might ask, well, binary search is really easy. Would I really ever bother to do this thing where I try to learn the index that's right for me and then use that, predicted learned index in order to jumpstart my binary search? And there's also been experimental work that shows that indeed this is, worth it when you have very large data sets. So in particular, experimental work has shown that you can outperform the baselines in speed by up to 70%, and that you can gain huge wins in memory as well. So just to summarize, what's the point with this example? The point is that you can do much better in binary search if instead of starting to look in the middle of your library, you started to look at the beginning because you had this additional information. So in particular, your win is from an order log n time algorithm to an order log error time algorithm. Okay, So I'm going to say for dictionary search for now, we're going to come back to this example a few times throughout the talk. And the next example I want to talk about is online load balancing or restricted assignment scheduling. Here, our jobs will arrive online, and we have machines available offline to process jobs. When a job arrives, it's equipped with a processing time, PJ, so how long it will take to process on a machine, and a list of machines that the job can be processed on. So our goal is to make these assignments as the jobs arrive in order to minimize the make span, which is a term I'm going to use a lot throughout this talk to refer to, the time that the last job is completed. So for a picture here, we have our 3 machines. These are available to us offline, and one by one, these jobs arrive. So let the length of this box indicate the length of the job. So this is a pretty long job. It can be processed on machines 1 or 3. And for now, I'm just going to do this how, I would do like a greedy algorithm if I were just trying to make these assignments. So it doesn't really matter to me since I have no information where this job goes for now. So I'll put it on machine 1. My next job arrives. Machine 1's already got a pretty long job on it, so let's put that on machine 2. Next job arrives. Again, machine 1's still busier than machine 2, so I'm going to put it on the machine 2. Next job arrives, and I don't really care between the two. Then I have this small job arrive. I'll put it on the machine I haven't used yet. And again, I'll put it on the machine with the least load. So with this greedy algorithm, we can get the solution over here to the left. But optimally, if I would have been, the price of the optimal offline solution would have been to completely equally balance these machines. So in particular, one can show that there is this log m lower bound for this online load balancing problem, meaning that an online algorithm is never going to be able to get competitive ratio better than log m, where m is the number of jobs that I've been given, or sorry, where m is the number of machines that I have. So, log 3 is not very big, but imagine this for, lots of machines, then, this grows a lot with m. So we can ask, okay, how did I mess up? Why am I maybe going to gain this log m factor? And in our small example that we saw here, part of the reason why is that machine 1 was actually a very contentious machine. Lots of jobs that arrive wanted to be placed on machine 1. And, in particular, every job that arrived, was able to be placed on machine 1, but contentiousness is a bit more tricky to clarify than that. So in particular, on machine 1, I assigned large early jobs that arrived to it, when maybe it would have been better to leave machine 1 open for jobs that ended up arriving later. So overall, a question is, what if we could predict how contentious a machine is? And then you can use that idea of how contentious a machine is to make better immediate assignments as you go, with the hope of producing a solution that has smaller make span. And indeed, you can do this. So a quantity that you can use to kind of predict or serve as a surrogate for how contentious the machines are a quantity that I'm going to call the machine weights. So these machine weights are values wi that will be assigned to each machine. Okay, so these are non-negative values. And if you assign a non-negative value to each machine, then you can get a fractional allocation x. And by that, I mean a fractional assignment of jobs to machines with the following procedure. Okay, so to assign, some load of job j to machine I, the weights w will let it be wi over, the weights of jobs in the neighborhood of j. So it's okay if you don't understand this quantity entirely. The point is that this quantity, there exists a good set of weights for any instance. So in particular, there exists a set of weights, W star, that produce fractional solution, given this, heuristic for producing fractional solutions, with make span at most 1 plus eta times the optimum. So you can get, arbitrarily close. So don't worry about this eta. This is just going to come into whatever, the like the runtime of like how you find this W star, just know that there exists some weights W star that give you like a very good fractional solution with good make span. So our question is if these machine weights can serve as a good indicator for how contentious a machine is and can help us to make fractional assignments which have good make span, then our question is, well, can we predict those good weights? So can we predict some W weights that are a good prediction for W star? And well, you should ask, well, what's good mean? Like, what does it mean to have a good prediction for W star? And so the error metric that was used is this, like for the max over all the machines, take WI over WI star, where you can assume without loss of generality that like W is greater than W star for all I. Okay. So what's the point? The point is that you can use these weights, or sorry, you can use your predictions for these weights to actually get a pretty interesting result. So if I fix an instance of jobs arriving on line J and assume I'm given weights W predicting W star that have error at most epsilon, where my error is this, quantity over here, then there's a simple way to like modify this kind of fractional allocation solution in order to get a fractional solution with make span at most log epsilon times the optimum. So you can only lose a factor of log epsilon as opposed to losing like maybe that factor of log m that we talked about before. So this is a fractional assignment, and then you can round it to an integral one with only loss log m. So in total, let's recall that the best you could do for online load balancing before wouldn't be to be with a lower bound of log m for m the number of machines. And now instead what we're saying is if you can get a prediction W of these weights W star, for W star being like this good fractional assignment, then there's kind of like a little bit of wiggling you can do with your prediction so that you can round to an integral solution that has make span at most log epsilon times log m times the optimum. So again, when log epsilon is a lot less than log m, you're making huge wins here in your competitive ratio. And I think that's what I want to say on online load balancing for now. I don't see any questions coming up, so I'll move on. Okay, so what have we done so far? I've just showed you two examples of learning augmented algorithms. This dictionary search, where your prediction is like predicting the index of the book that you actually wanted to find, and then online load balancing, which is a little bit more complicated. And instead, you're kind of predicting this quantity called the machine weights, where the machine weights help you design a good fractional solution. So we talked about this in examples first, and now I want to tell you like a more formal definition of learning augmented algorithms and talk a little bit more about these predictions. So I gave you these two sentences before, and we're gonna, keep these two sentences in mind if you ever kind of lose track of what's happening here. So overall, let's assume that we fix a problem, just like, any problem, maybe like that scheduling problem, dictionary search, or something else, and fix an instance space X, where all the instances of your problems lie, maybe with some like, kind of fixed parameters. Like maybe in the online scheduling, I've like fixed the like number of jobs and number of machines, and maybe it's just like the edges between them that change. And further fix what we'll call the prediction metric space. So the prediction space is going to be on this space Y, equipped with this loss function L. And what's going to happen is we're going to view the prediction with these two different functions. The first is L, and then the second is this predictor P, where P is going to be a map from an instance to a prediction P of X. And P of X is going to serve as the prediction for some underlying quantity sigma of X, which is unknown to us but lies in this space. And sigma of X is going to be like the thing that you wanted to predict. It's going to be like in dictionary search, it's going to be the exact index of where the book was. in the load balancing example, it's going to be like those really good weights W star. And now, because of this loss function, you can look at the distance between P of X and sigma of X. So let's say this with our words now. The predictor is going to be the pair of functions, P with L, where P is a function from X to Y, from the instance space on, from the instance space to like the prediction space. And P of X gives the prediction for the best value for X in Y. So it's the prediction of sigma X. Then the error in the prediction, you can look at as being, the max over all of the instances between the distance between sigma X and P of X. So this is, this is more formal than just going over examples. This is still pretty informal. This is like, the easiest way I think to kind of view this in a talk for now. Okay, so great. We talked about our, instance space predictions, but I haven't said anything about, the algorithm part of it. So what is the algorithm? How is the algorithm going to use these predictions? Our algorithm, alg, is going to have access to that quantity P of X, so to that predicted quantity, for instance, X. And now you can, take whatever metric you're working with, competitive ratio, whatever. And then what you can do is if P has that the error is at most epsilon, then you can measure, like the competitive ratio that this algorithm gets with the prediction by looking over all of the instances and measuring the algorithm's performance on X with prediction P as compared to, the best optimal offline thing. Okay, so we'll say exactly what that means, kind of referring back to our examples now. So for our dictionary example, my instance space, for instance, is size and dictionaries. My predicted labels are, the predicted instances where I could be trying to find my book at. And then the loss between my indices is just going to be, the absolute value between them. And then the error is just, that between, the predicted position of the book versus the actual position of the book. So in our example, we predicted that the index that we wanted was index 2, but actually it was index 3. Whoops, that was a little fast. And so the point is that what does the algorithm do? The algorithm is given access to a predictor that has like, at most some error epsilon, and then you can give guarantees on the algorithm based on its like, epsilon good predictor. So we'll keep on going over these kind of prediction examples, but we've kind of laid out what is a prediction, what is a learning augmented algorithm, but we haven't really talked a lot about more properties of the prediction. Okay, so in particular, like what makes a good prediction? We talked about it being like, the index of the book you're looking for dictionary search, or, like those machine weights for online load balancing. But who's to say it shouldn't have been like, some other quantity, or that there's not other predicted quantities that work for those problems? Okay, so we'll look at this, like what has been focused on in the literature for good properties of predictions. And for now, keep this yellow box in the corner in mind. We're going to assume that for all of your inputs X, the prediction has error at most epsilon. Okay, and by that prediction having error at most epsilon, we mean that this loss function between P and sigma for any X is going to be at most epsilon. Okay, so in the literature, there's been primarily 3 points that have been focused on. The first is consistency. So consistency means that the algorithm has to perform well when you're given like that perfect prediction. Okay, so when P of X is equal to sigma of X, then you want to be very happy with your algorithm guarantees. So in dictionary search, this is like very easy to see. Here, your runtime of your binary search would be now like 0 steps because you just like predicted the right instance. And then even for load balancing too, it's kind of the same thing. If you predict those really good weights W star, then your competitive ratio is only log M. It's only like that loss in the fractional rounding to integral rounding bit. Now for robustness, You want the algorithm's performance to degrade, we use the phrase like degrade gracefully with epsilon in the literature. By degrade gracefully, we basically mean that the further away P of X moves from sigma of X, you don't want that to like blow up necessarily. So as P of X moves away, like as soon as you introduce any error, you want it to be able to like deal with that error in a okay manner. So in other words, if you don't predict P of X to be equal to sigma of X, if you predict it with like a little bit outside of that, you don't want your whatever competitive ratio runtime to immediately blow up. So in dictionary search, we saw that with some error with positive epsilon, the runtime was like order log epsilon. And then I don't have room for the picture here, but the last one is competitive. So competitive means that when the algorithm receives like an absolute garbage prediction, it doesn't perform much worse than if it wouldn't have been given any prediction. So the picture here is that as P of X like runs away from sigma of X and does whatever it wants, like if you give me a totally garbage prediction for an instance, it's fine. Your algorithm is still going to be able to, give you something that you're not too upset with. So in dictionary search, this one was pretty easy because you're never going to do, like a constant factor worse than just order log n. All right, so in the literature so far, we have these 3 properties: consistency, robustness, and competitiveness. These have been like the primary focus of the properties of what makes a good prediction. And you might look at this, and if I had more time and I told you to think about it a little bit more, you might notice that some things are missing from this list. So, take like 5 seconds, stare at this list, and see if you can come up with anything that's, missing. So one thing that's been missing from this list, which is talked about in the literature to some extent, but probably not as forthright as it should be, is learnability. So how in the world are you going to get this P? Like, how are you going to get this prediction? In particular, like, why can't I just predict the optimal offline solution or something? Okay. And the reason, why you're like, well, that's like cheating to predict the optimal offline solution is because like it's something that for most problems, you're just never going to have access to that. Okay. So learnability, a lot of the papers in the literature do a good job discussing the learnability component of the prediction. And there's like 3 ways that learnability kind of goes right now in the literature. The first is just like total neural network magic that I, don't really understand a lot right now in this moment, but I look forward to understanding it in the future. The second is this kind of like pack learning framework. So if you have some distribution over the space X, then what you can do is you can sample from X, and you can take enough samples so that you've learned like a prediction, which I'm going to call P now, not depending on X. You've learned a prediction P that's close to like the best thing you could do in expectation for your whole distribution. So like sigma is like the best parameter that you could give, like over like the whole distribution, and you're going to learn something close to that. So again, kind of like a pack learning result there. And something which I would like to, talk a little bit more about as we go is the fact that like your instances might not necessarily follow like a specific distribution, but it might be the case that today's instance looks very similar to yesterday's instance. And so in particular, you're able to like take an instance that you learned yesterday and you can reuse it today. Or maybe I said that wrong. You can take an instance from yesterday and you can use the predictor for, yesterday's problem on today's data. So anyway, that's learnability. I made it its own little point because I wanted to point out that 1, it's important, and 2, it's often somehow like people leave it out sometimes, which, maybe we shouldn't be doing when we talk about, predictions. And then the second piece that I would like to argue is missing from this list, but it has not been studied nearly as much as any of these, is instance robustness. So we'll talk about instance robustness next. Okay. So we have this picture before to kind of talk about our, problem space, our prediction space, this function P with the loss function L. And I'd like to talk about how instance robustness plays into this picture. Okay, so, sorry, we had this picture here before, and we were only really concerned about having like a distance function equipped on the prediction space. But in instance robustness, what I actually want to do is I'm concerned with being able to use the prediction for an instance on nearby instances. So let's look at the picture first. If I can equip a distance function on my instance space, remember which one was x and which one was x prime. Whatever. So if my instance x and my instance x prime are close to each other, then in an instance robust prediction, you would have that sigma x is close to sigma of x prime, which means that if the predictor p of x is a good prediction for sigma of x, then it's also a pretty good prediction for sigma of x prime. And so the point is that you can like recycle your predictions in a way that like isn't necessarily captured by just having like some underlying distribution over your instances necessarily. So in words, for some problems, for PL to be a good prediction, you need sigma x close to sigma of x prime when x is close to x prime. So in particular, yeah, prediction x is good for x in your algorithm, then it's also a good prediction for the nearby instance x prime. And so as I kind of said on the last slide, the motivation for this comes from the idea that today's instance might look a lot like yesterday's instance. So in particular, especially in like clustering, actually in like the clustering workshop 2 weeks ago, when I was asking Vincent a question on this after his talk, he like exactly said this without prompting from me, and I felt very, felt very happy. He was exactly saying that, part of what you want when you design clustering sometimes is the ability for them not to change too much when you slightly perturb the instance. And you could think of this as really saying that like if you're like predicting like the cluster labels, you want the cluster labels to not change too much, or you want the cluster labels to not be too bad for an instance where you've like, like twiddled the, the points slightly. So I think that's all I want to say for like the introduction of instance robustness. I'll just pause for a sec in case anyone wants to type another question in the chat. Okay. So, I've introduced this notion of instance robustness. Let's see it with our dictionary search example just to make sure it's like really cemented in here. So again, here is our dictionary search. Nearby instance, it's not like as motivating with dictionary search because why would you necessarily be looking for like 2 books near each other? I don't know, maybe you like really like Lewis Carroll and so you're looking for other books by Lewis Carroll or something. Let's say that, in addition to your book by Lewis Carroll, you're also looking for a book by Charles Dickens. Okay, so again, you're looking for a book by Charles Dickens, and what you're going to do is, after you find your book by Lewis Carroll, you're not just going to, start over and do like binary search from the beginning again. And there's also even no need to gain a new prediction about like where this book by Charles Dickens is, because you know that, the book by Charles Dickens should be very close to the book by Lewis Carroll. So you could just use your same prediction as before. And so in using this, same prediction, you are able to like, still do like a faster binary search. So again, the distance function on the instances, here it makes sense just to be like the, the difference, like the difference between like the indices of the instances. And, if the difference between the instances is at most like delta away, meaning the books are delta apart, then you could just bound your, like the runtime of your binary search by log epsilon plus delta. Or again, epsilon is like the error between the prediction and like the the best quantity you could have, and then delta is like, that remaining distance between the instances. So this is instance robustness. And overall, like, instance robustness is well motivated in the way that instances can look similar, but this isn't modeled by underlying distribution on the instance space. It's kind of already used in practice if you think about it, which isn't something I ever like hear people talked about, but it's you can think of it as being used in practice as like the warm start heuristic. So it's a warm start heuristic. In practice, like, you'll often use like an initial guess for a solution. Based on the initial guess, you have like a nearby solution. Okay, so in a sense, this is kind of saying that your solutions are like your instance robust predictions, which is interesting. And three, there's this important piece to good predictions of learnability, and learnability is sometimes glossed over in the literature. And if you have an instance robust prediction, then you also have learnability. So, or at least like that's the way I'm saying the implication. It's a little bit more complicated than that. But point is, it can help kind of fill in this gap of a learnable prediction. Okay, so again, instance robustness, it doesn't necessarily make sense for all problems, but the instances I pointed out, like clustering, scheduling, online matching, these are instances where like it truly seems to make sense. Like, you might be looking at instances in practice that like look very similar to each other. All right, so what I'm going to do next is, so this instance robustness was introduced by this group of authors, and this has been like kind of the only work done on instance robustness so far that I'm almost certain of that, but at least that I'm aware of. And I want to show you like an instance robustness result, and just kind of explain to you why it's like has some very interesting properties, and I'm interested in studying it further. Okay, so last part of the talk, we'll just talk about instance robustness for, I don't know, what time's this done? 8:10. So we'll talk about instance robustness for 10-ish minutes, and I'll wrap up, and then we'll call it. All right, so recall our online load balancing problem where we have these machine weights, W, which can then give you a fractional allocation between jobs and machines. So let's introduce a little bit of notation here to talk about instance robustness in this problem. So let S to the J sub L be the sum of the processing lengths of jobs of type L in the instance J. So this big J is meaning, the set of the set of jobs that are arriving equipped with their processing times and the jobs that they can be processed on. Jobs of type L, we'll say that two jobs are of the same type if they can be processed on the same set of machines. So in our old instance, we had this little job and this big job that could both go on machines 1 and 3. So these jobs are of the same type. Remember that our whole point is we're going to look on the instance space now, and we're going to try to measure the distance between two different instances. And it is non-trivial here to come up with a good distance metric between instances that kind of like plays well with your like predictions. So anyway, the distance metric that they came up with is the distance between the two instances. I shouldn't have denoted this like this. This is really the distance between J and J prime, is taking the max over all the job types of the max of the ratios of either S sub L to the J divided by S sub J prime sub L, or flip that ratio. So just focus on one of these. It's saying between instances J and J prime, how much do the jobs of type L change? And that could mean that you just change processing lengths of jobs of type L. It could mean that you take a job of type L prime and you change it to a job of type L by removing an edge or something like that. So it's, it's a pretty robust metric for how you can, look at the difference between instances. So in particular, let's assume that this was my instance J. And then if I add this job to form the instance, J prime, then note that, the total length has increased from, the sum of these two to the sum of these three, which doesn't change by too much. It's like at most a factor two. But if I had these two jobs and then I, moved some things around, or I like made processing time smaller so that I only have like this very, very tiny job of this type, then I'm going to see this be very, very large, right? Because I have this like, this very large sum of the processing lengths divided by this like very small thing. So this is like the distance metric that we're going to look at. All right, so letting L of J of W be the fractional makespan of instance J using weights W, which you get by doing like, this fractional load here. Then what the set of authors showed is that for an instance of jobs J, such that the fractional makespan of J using the weights W, if that's at most like a 1 plus eta off from the optimal, then the nearby instance J prime has fractional makespan at most a 1 plus eta squared times the distance squared off from the optimum. So don't really worry about the 1 plus eta. The important thing here is that we're saying that if I use weights that are good for J on my nearby instance J prime, that I'm going to lose this like distance squared. So I actually don't know if I want to talk about the proof, just given time. I think I will not do it in like huge detail. But all I really wanted to get out with the proof is that the proof is really not that difficult. You're kind of just symbol pushing. So what you can do is you can look at the load on a single machine I, and overall you can show that like if I use the W prime weights for J, that's going to be at most D times using the W prime weights for J prime. And then similarly, if you're using the W weights for J prime, you can show that's at most using D times, the load on machine I for using the W weights for J. And so I was just like, kind of like proving this result here. And all I had wanted to get out of showing you this proof is something that's very weird about this proof is the fact that this will actually hold for any like fractional assignment with makespan at most 1 plus eta opt. So what that means is that the weights aren't actually coming into the picture at all here. All that the weights are doing is giving you this like good fractional assignment. But any other predicted quantity that'll give you a good fractional assignment, this like, instance robustness piece also holds. So this is interesting because it says it's maybe not using like the the prediction isn't really coming into the instance robustness piece here. And there's also something a little bit funny about this instance robustness definition that I wanted to point out in case anyone had been thinking it themselves. So recall that this is our distance between our instances J and J prime. We're looking at the max ratio between the sizes of jobs of type L. And what really happens with the way, because you're computing a ratio here, is you're not allowed, if I had like, this job which was going to all three of these machines, I'm not allowed to like remove an edge if it creates a new job type. So I cannot add any new job types with this distance because otherwise I end up with something divided by 0. And in particular, there's not like an easy way to fix this distance metric and let the previous proof, which I didn't have time to show you, get pushed through. So the point is that there's something kind of sneaky going on with these distance metrics, and that it's not necessarily clear how to come up with a distance metric that plays well on the instance space, but that also kind of like works well with your corresponding function L on the prediction space. So maybe one kind of question moving forward from here is, can you build fractional assignments X that have, good makespan, which is more robust to instance perturbations? And more robust would mean, they already came up with like a pretty robust one, but could you do something where you're allowed to add new job types? So I told you there was only, like Instance robustness hasn't been super well studied yet, or at least not in the way that it's called by that name, but it has come up in like a large array of the problems without ever having used that word to describe it. So there's this K-means paper that came out where what you're predicting is like your prediction is the labels of points, such that at most like a small fraction of of the points can be mislabeled. And one of the ways that they justify that you're able to obtain such a prediction is from using like an old clustering, which in particular would be like literally saying that you need this prediction to be instance robust. There's also been work on minimizing total completion time and non-clairvoyant scheduling. Non-clairvoyant scheduling is when jobs arrive and you don't know the processing length of them. So you just have to start running the job, and it's only when the job is completed that you learn its processing length. So here, what has already been studied, but again, not said in this language, is that for this problem, predicting like the job's length, so predicting like the job's lengths that will arrive, is a very non-instance robust, and it's caused like kind of a lot of problems in studying this problem. Again, there's something weird going on with caching versus weighted caching, where there is a prediction for caching, which works very well and is very robust, both to changes in the prediction and changes in the instance. But in weighted caching, it's like a much more complicated story. This does not seem to be true at all. And lastly, correlation clustering. Again, there's like, you can look at like a couple different obvious predictions that could be studied, and some of them are clearly instance robust and some of them are not. And the good predictions are the ones that are instance robust. So it seems to be like, for some problems, a good way of kind of separating your good predictions from your less good predictions. So yeah, I kind of skipped over the past few slides just for the sake of time, but all I want you to get out of these examples are the following. That some predictions in the literature are instance robust and some are not. For some problems, instance robustness helps distinguish helpful predictions. And coming up with these distance metrics that play nice on the instance space is very challenging. Or sorry, the distance metrics playing nice on the instance space. And this is like compatible with the metrics on the prediction space. So again, this like the metric D playing well with the metric L. This is like very challenging. So the point being that there's like a lot of open problems you could ask here just from looking at the literature which already exists. So wrapping up, as I said, my goal for this talk was just to give a very friendly overview into learning augmented algorithms, and then whatever, spend the last little bit of it talking about this instance robustness property that I think is interesting and understudied. But more specifically, talking about the predictions, designing good predictions is difficult and interesting. And for some problems, predictions should be instance robust, or robust to small perturbations in the problem instance. And I'll just end with some interesting open questions here. I guess in particular, I'll just point out this first open question, that in this space, there's definitely a need for more like rigorous theoretical foundations in order to really make this space like, I don't know, here for the long haul or something. But I think that's it. So yeah, thank you so much for your attention.